In these two examples, we knew which way to expect the reaction to go because we only started with reactants. But in some cases, you might actually have a combination where both the reactants and the products are present in the reaction medium. So how to make a prediction about the direction of the reaction in this case? Calculate the reaction quotient, which is the actual ratio between the reactant concentration and the product concentration in the given combination before the system reaches equilibrium. Your reaction quotient is smaller than the actual equilibrium constant for the reaction, and in this case, the system will have to go to the right-hand side to make more products to make the ratio go up till it equals the equilibrium constant for this reaction. If your reaction quotient is equal to the equilibrium constant, it means that the system is already at equilibrium. So no change is going to be needed. If the reaction quotient is larger than the equilibrium constant, it means that the system has much more products than it needs, which means the reaction will get shifted to the left-hand side to consume some of the products and convert them back to reactants till the ratio gets down to equal the equilibrium constant for the reaction. So for this example right here, we have a combination of both the reactants and the products in the same container. So in order to make a prediction about the direction of the shift for the reaction, we'll have to calculate the reaction quotient and compare it to the equilibrium constant. So first we set up the reaction quotient expression. So reaction quotient for the reaction is going to equal the actual ratio of concentrations for the products, which is going to be raised to the power 2, because you have 2 moles in the reaction divided by the concentration of the reactants and hydrogen raised to the power of 3. The concentration of ammonia is 0.5 divided by the volume of the container, which is going to be 0.01 molar to the power 2. Concentration of nitrogen is 1 mole divided by the volume of the container, which is 50 liter, is going to give you 0.02 molar. And concentration of hydrogen is 0.06 mole to the power 3. And we calculate the value using these numbers here is going to give you 23.15, which is significantly larger than the actual equilibrium constant of the reaction, which is supposed to be 0.5. In this case, as we said, if you have a reaction quotient that is significantly larger than the equilibrium constant itself, the reaction will have to go backward to the left-hand side to consume some of the excess product and convert it back to reactants till it makes a ratio of concentrations equal the equilibrium constant ratio. So that's the direction of the shift that we expect. And we start applying the ICE strategy. So you have initial condition with 0.02 of nitrogen, 0.06 of hydrogen, 0.01 of ammonia. And as we said, we expect the reaction to go back to the left-hand side to consume some of the ammonia. So 2x of ammonia will be consumed and or decomposed, which will produce 3x of hydrogen because the ratio is 3 to 2, and 1x of nitrogen. So that's the change that we expect. That change will keep going till the system reaches equilibrium. And at equilibrium, the concentration of nitrogen is going to be the initial concentration plus a change, the initial concentration plus a change. And here is the initial concentration minus a change for ammonia. And we will use these equilibrium concentrations in the reaction equilibrium constant expression. So it's going to be these concentrations right here. So it's going to be 0.01 minus 2x squared divided by 0.02 plus x for nitrogen times 0.06 plus 3x to the power 3 for hydrogen, and that is going to equal the value for the equilibrium constant, which is 0.5. Now we have an equation in x, so we solve for x, and this is what we get. Only reasonable root that is going to equal 0.0079. And based on this, you can calculate the equilibrium concentration for all the species, because nitrogen concentration at equilibrium is going to equal the initial concentration plus the change that happened, 0.02 plus 0.0079. Hydrogen is going to be the initial concentration plus 3x, so it equals 0.06 plus 3 times 0.0079, and so on.